This is Theory and Calculation of Transient Electric Phenomena and Oscillations by Charles Steinmetz. Check the comments for timestamps and information regarding the future of my channel and this project. Chapter 1. Chapter in the Constants of the Electric Circuit. 1. To transmit electric energy from one place where it is generated to another place where it is used, an electric circuit is required, consisting of conductors which connect the point of generation with the point of utilization. When electric energy flows through a circuit, phenomena take place inside of the conductor as well as in the space outside of the conductor. In the conductor, during the flow of electric energy through the circuit, electric energy is consumed continuously by being converted into heat. Along the circuit, from the generator to the receiver circuit, the flow of energy steadily decreases by the amount consumed in the conductor, and a power gradient exists in the circuit along or parallel with the conductor. Thus, while the voltage may decrease from generator to receiver circuit, as is usually the case, or may increase, as in an alternating current circuit with leading current, and while the current may remain constant throughout the circuit, or decrease, as in a transmission line of considerable capacity with a leading or non-inductive receiver circuit, the flow of energy always decreases from generating to receiving circuit, and the power gradient therefore is characteristic of the direction of the flow of energy. In the space outside of the conductor, during the flow of energy through the circuit, a condition of stress exists which is called the electric field of the conductor. That is, the surrounding space is not uniform, but has different electric and magnetic properties in different directions. No power is required to maintain the electric field, but energy is required to produce the electric field, and this energy is returned more or less completely when the electric field disappears by the stoppage of the flow of energy. Thus, in starting the flow of electric energy before a permanent condition is reached, a finite time must elapse during which the energy of the electric field is stored, and the generator therefore gives more power than consumed in the conductor and delivered at the receiving end. Again, the flow of electric energy cannot be stopped instantly, but first the energy stored in the electric field has to be expended. As a result hereof, where the flow of electric energy pulsates, as in an alternating current circuit, continuously electric energy is stored in the field during a rise of the power and returned to the circuit again during a decrease of the power. The electric field of the conductor exerts magnetic and electrostatic actions. The magnetic action is a maximum in the direction concentric, or approximately so, to the conductor. That is, a needle-shaped magnetizable body, as an iron needle, tends to set itself in a direction concentric to the conductor. The electrostatic action has a maximum in a direction radial, or approximately so, to the conductor. That is, a light needle-shaped conducting body, if the electrostatic component of the field is powerful enough, tends to set itself in a direction radial to the conductor, and light bodies are attracted or repelled radially to the conductor. Thus, the electric field of a circuit over which energy flows has three main axes which are at right angles with each other: the electromagnetic axis, concentric with the conductor; the electrostatic axis, radial to the conductor; the power gradient, parallel to the conductor. This is frequently expressed pictorially by saying that the lines of magnetic force of the circuit are concentric, the lines of electrostatic force radial to the conductor. Where, as is usually the case, the electric circuit consists of several conductors, the electric fields of the conductors superimpose upon each other, and the resultant lines of magnetic and of electrostatic forces are not concentric and radial respectively, except approximately in the immediate neighborhood of the conductor. In the electric field between parallel conductors, the magnetic and the electrostatic lines of force are conjugate pencils of circles. 2. Neither the power consumption in the conductor, nor the electromagnetic field, nor the electrostatic field are proportional to the flow of energy through the circuit. The product, however, of the intensity of the magnetic field represented as phi and the intensity of the electrostatic field represented as psi is proportional to the flow of energy, or the power, denoted as P. The power P is therefore resolved into a product of two components, I and E, which are chosen proportional respectively to the intensity of the magnetic field phi and of the electrostatic field psi. That is, putting the power P as equal to the product of I and E, we have the following relationships. Phi is equal to L times I and represents the intensity of the electromagnetic field. Psi is equal to C times E and represents the intensity of the electrostatic field. The component I, called the current, is defined as that factor of the electric power P, which is proportional to the magnetic field, and the other component E, called the voltage, is defined as that factor of the electric power P, which is proportional to the electrostatic field. Current I and voltage E, therefore, are mathematical fictions, factors of the power P, introduced to represent respectively the magnetic and the electrostatic or dielectric phenomena. The current I is measured by the magnetic action of a circuit, as in the ammeter. The voltage E by the electrostatic action of a circuit, as in the electrostatic voltmeter, or by producing a current I by the voltage E and measuring this current I by its magnetic action in the usual voltmeter. The coefficients L and C, which are the proportional factors of the magnetic and of the dielectric component of the electric field, are called the inductance and the capacity of the circuit, respectively. As electric power P is resolved into the product of current I and voltage E, the power loss in the conductor, represented as P sub L, therefore can also be resolved into a product of current I and voltage E sub L, which is consumed in the conductor. That is, the power loss P sub L is equal to the product of I and E sub L. It is found that the voltage consumed in the conductor, represented as E sub L, is proportional to the factor I of the power P. That is, E sub L is equal to R times I, where R is the proportionality factor of the voltage consumed by the loss of power in the conductor, or by the power gradient, and is called the resistance of the circuit. Any electric circuit, therefore, must have three constants, R, L, and C, where R is the circuit constant representing the power gradient, or the loss of power in the conductor, called resistance. L is the circuit constant representing the intensity of the electromagnetic component of the electric field of the circuit, called inductance. C is the circuit constant representing the intensity of the electrostatic component of the electric field of the circuit, called capacity. In most circuits, there is no current consumed in the conductor, represented as I sub L and proportional to the voltage factor E of the power P. That is, I sub L is equal to G times E, where G is the proportionality factor of the current consumed by the loss of power in the conductor, which depends on the voltage, such as dielectric losses. Where such losses exist, a fourth circuit constant appears, called the conductance G. For further details, refer to sections 3 and 4. 3. A change of the magnetic field of the conductor, that is, if the number of lines of magnetic force phi surrounding the conductor changes, generates an electromotive force denoted as E prime, which is equal to the derivative of phi with respect to time. Thus, E prime is equal to the rate of change of phi over time, and the conductor absorbs a power P prime, which is equal to I times E prime. Substituting, this becomes I times the rate of change of phi over time. Using the relationship where phi is equal to L times I, we find that the rate of change of phi over time is equal to L times the rate of change of I over time. Substituting back, we find that the power P prime is equal to L times I times the rate of change of I over time. The total energy absorbed by the magnetic field during the rise of current from 0 to I is represented as W sub m and is calculated as the integral of P prime over time. This simplifies to L times the integral of I with respect to I. That is, the energy stored in the magnetic field of the circuit, represented as W sub m, is equal to 1/2 of I squared times L. A change of the dielectric field of the conductor, represented as psi, absorbs a current proportional to the change of the dielectric field. This current is denoted as I prime and is equal to the rate of change of psi with respect to time. The power absorbed by this process, represented as P double prime, is equal to E times I prime, or equivalently E times the rate of change of psi with respect to time. Using the relationship where psi is equal to C times E, we substitute to find that the power P double prime is equal to C times E times the rate of change of E with respect to time. The total energy absorbed by the dielectric field during a rise of voltage from 0 to E is represented as W sub k and is calculated as the integral of P double prime over time. This simplifies to C times the integral of E with respect to E. That is, the energy stored in the dielectric field, represented as W sub k, is equal to 1/2 of E squared times C. The power consumed in the conductor by its resistance, represented as R, is denoted as P sub R and is equal to I times E sub L. Substituting, we find that P sub R is equal to I squared times R. Thus, when the electric power, represented as P, is equal to E times I, the following components exist in a circuit. The power lost in the conductor is represented as P sub R and is equal to I squared times R. The energy stored in the magnetic field of the circuit is represented as W sub M and is equal to 1/2 of I squared times L. The energy stored in the dielectric field of the circuit is represented as W sub K and is equal to 1/2 of E squared times C. Three circuit constants, resistance denoted as R, inductance denoted as L, and capacity denoted as C, therefore appear as the components of energy conversion into heat, magnetism, and electric stress, respectively, in the circuit. 4. The circuit constant resistance, denoted as R, depends only on the size and material of the conductor, but not on the position of the conductor in space, nor on the material filling the space surrounding the conductor, nor on the shape of the conductor section. The circuit constant's inductance, denoted as L, and capacity, denoted as C, almost entirely depend on the position of the conductor in space, on the material filling the space surrounding the conductor, and on the shape of the conductor section, but do not depend on the material of the conductor, except to a small extent as represented by the electric field inside the conductor section. 5. The resistance, denoted as R, is proportional to the length and inversely proportional to the section of the conductor. This relationship is expressed as R equals rho times the length divided by the area, where rho is a constant of the material, called the resistivity or specific resistance. For different materials, the value of rho varies probably over a far greater range than almost any other physical quantity. Expressed in ohms per cubic centimeter, it is approximately as follows at ordinary temperatures. Metals. Copper is 1.6 times 10 to the power of negative 6. Aluminum is 2.8 times 10 to the power of negative 6. Iron is 10 times 10 to the power of negative 6. Mercury is 94 times 10 to the power of negative 6. Gray cast iron is up to 100 times 10 to the power of negative 6. High resistance alloys are up to 150 times 10 to the power of negative 6. Electrolytes. Nitric acid at 30% concentration is as low as 1.3. Potassium hydroxide at 25% concentration is as low as 1.9. Sodium chloride at 25% concentration is as low as 4.7. Values increase from pure river water and extend over alcohols, oils, and similar materials to practically infinity. Note, these values assume a conductor of 1 centimeter length and 1 square centimeter cross-sectional area. So-called insulators have resistivity values as follows. Fiber is approximately 10 to the power of 12. Paraffin oil is approximately 10 to the power of 13. Paraffin ranges from approximately 10 to the power of 14 to 10 to the power of 18. Mica is approximately 10 to the power of 14. Glass ranges from approximately 10 to the power of 14 to 10 to the power of 18. Rubber is approximately 10 to the power of 10. Air is practically infinite in resistivity. In the wide gap between the highest resistivity of metal alloys, about 150 times 10 to the power of negative 6, and the lowest resistivity of electrolytes, about 1, we find the following. Carbon. Metallic carbon has a resistivity as low as 100 times 10 to the power of negative 6. Amorphous dense carbon has a resistivity starting at 0.04 and higher. Anthracite carbon exhibits very high resistivity. Silicon and silicon alloys. Cast silicon has varying resistivity. Ferrosilicon ranges from 0.04 down to 50 times 10 to the power of negative 6. The resistivity of arcs and of Geissler tube discharges is of about the same magnitude as electrolytic resistivity. The resistivity, represented as ρ, is usually a function of temperature. It rises slightly with an increase in temperature in metallic conductors, but decreases in electrolytic conductors. Only with a few materials, such as silicon, does the temperature variation of ρ become so significant that ρ can no longer be considered approximately constant for all currents which produce a considerable temperature rise in the conductor. Such materials are commonly referred to as pyroelectrolytes. 6. The inductance, represented as L, is proportional to the section and inversely proportional to the length of the magnetic circuit surrounding the conductor. It can be expressed as L equals mu times the area divided by the length, where mu is a constant of the material filling the space surrounding the conductor and is called the magnetic permeability. As in general, neither section nor length is constant in different parts of the magnetic circuit surrounding an electric conductor. Circuit has as a rule to be calculated piecemeal or by integration over the space occupied by it. The permeability represented as mu is constant and equals unity, or very closely mu equals 1 for all substances, with the exception of a few materials referred to as magnetic materials such as iron, cobalt, nickel, and similar substances. In these materials, permeability is significantly higher, reaching values as high as 6,000, and under certain conditions in iron, as high as 30,000. In magnetic materials, the permeability, mu, is not constant but varies with the magnetic flux density, which is the number of lines of magnetic force per unit section represented as theta, and decreases rapidly for high values of theta. In such materials, the term mu becomes inconvenient, and the inductance, represented as L, is calculated using the relation between the magnetizing force, given in ampere turns per unit length of the magnetic circuit, referred to as field intensity, and magnetic induction. The magnetic induction, represented as Q in magnetic materials, is the sum of the space induction, represented as H, corresponding to unit permeability, plus the metallic induction, represented as B prime, which reaches a finite limiting value. That is, the magnetic induction Q is equal to H plus B prime. The limiting values, or so-called saturation values, of B prime are approximately as follows, in lines of magnetic force per square centimeter. Iron is 21,000, cobalt is 12,000, nickel is 6,000, magnetite is 5,000, manganese alloys can be up to 5,000. The inductance, represented as L, is a constant of the circuit if the space surrounding the conductor contains no magnetic material. However, if magnetic material exists in the space surrounding the conductor, the inductance becomes more or less variable with the current, represented as I. In such cases, as the current I increases, the inductance L first slightly increases, then reaches a maximum, and subsequently decreases, approaching as a limiting value the inductance it would have if no magnetic material were present in the space surrounding the conductor. On the above page, B should be understood as magnetic induction, not Q or any other letter, which was read in error. B, magnetic induction in the material, is simply the product of mu, the permeability of the material, and H, the density of magnetic lines of force in air. Since the density increases due to magnetic induction, this increase in density is expressed as the constant mu. Please check other related videos on my channel. Links are provided in the description. The capacity, represented as C, is proportional to the section and inversely proportional to the length of the electrostatic field of the conductor. This relationship is expressed as C equals kappa times the area divided by the length, where kappa is a constant of the filling the space surrounding the conductor. This constant is referred to as the dielectric constant, specific capacity, or permittivity. Usually, the section and length of different parts of the electrostatic circuit vary, and the capacity therefore must be calculated piecemeal or by integration. The dielectric constant, represented as kappa, varies only over a relatively narrow range across different materials. It is approximately as follows. Kappa equals 1 in a vacuum, in air, and in other gases. Kappa ranges from 2 to 3 in oils, paraffins, fibers, and similar materials. Kappa ranges from 3 to 4 in rubber and gutta percha. Kappa ranges from 3 to 5 in glass and mica. Kappa can reach values as high as 7 to 8 in organic compounds of heavy metals, such as lead stearate, and approximately 12 in sulfur. The dielectric constant, kappa, is practically constant for all voltages, represented as E up to that voltage at which the electrostatic field intensity, or the electrostatic gradient measured as volts per centimeter, exceeds a certain value represented as delta. This value, delta, depends on the material and is called the dielectric strength or disruptive strength of the material. At this potential gradient, the medium breaks down mechanically by puncture and ceases to insulate, allowing electricity to pass and equalizing the potential gradient. The approximate disruptive strengths, represented as delta and measured in volts per centimeter, are as follows. Air has a disruptive strength of 30,000. Oils range from 250,000 to 1 million. Mica can reach up to 4 million. The capacity, represented as C of a circuit, is constant up to the voltage E at which, in some part of the electrostatic field, the dielectric strength is exceeded. At this point, disruption occurs, rendering part of the surrounding space conductive. This increases the effective size of the conductor and thereby increases the capacity, C. 8. Of the amount of energy consumed in creating the electric field of the circuit, not all is returned upon the disappearance of the electric field. A part of this energy is consumed by conversion into heat or by changing the electric field in other ways. That is, the conversion of electric energy into and from electromagnetic and electrostatic stress is not entirely complete, and energy loss occurs. This is especially notable with the magnetic field in so-called magnetic materials and with the electrostatic field in non-homogeneous dielectrics. The energy loss associated with the production and reconversion of the magnetic component of the field can be represented by an effective resistance, denoted as R prime, which adds to the resistance of the conductor, R sub 0, and thereby increases it. The energy loss in the electrostatic field can be represented by an effective resistance, denoted as R double prime, which acts as a shunt across the circuit and consumes an energy current, denoted as I double prime, in addition to the current I in the conductor. Typically, instead of using the effective resistance R double prime, its reciprocal is used, and the energy loss in the electrostatic field is represented by a shunted conductance, denoted as G. In its most general form, the electric circuit therefore contains the following constants. 1. Inductance, represented as L, stores energy equal to 1/2 of I squared times L. 2. Capacity, represented as C, stores energy equal to 1/2 of E squared times C. 3. Resistance, represented as R, which is equal to R sub 0 plus R prime, consumes power equal to I squared times R. This can be further broken down as I squared times R sub 0 plus I squared times R prime. 4. Conductance, represented as G, consumes power equal to E squared times G. Here, R sub 0 represents the resistance of the conductor, R prime represents the effective resistance accounting for power loss in the magnetic field L, and G represents the power loss in the electrostatic field C. 9. If, among the three components of the electric field, namely the electromagnetic stress, the electrostatic stress, and the power gradient, any one of them equals 0, a second component must also equal 0. In other words, either all three components are present or only one exists. Electric systems in which the magnetic component of the field is absent, while the electrostatic component may be considerable, are exemplified by an electric generator or a battery operating on an open circuit, or by an electrostatic machine. In such systems, the disruptive effects caused by high voltage therefore, are most pronounced while the power is negligible, and phenomena of this character are usually referred to as static. Electric systems in which the electrostatic component of the field is absent while the electromagnetic component is considerable are exemplified by the short-circuited secondary coil of a transformer. In such systems, no potential difference exists, and consequently, no electrostatic field, as the generated electromotive force is entirely consumed at the place of generation. The electrostatic component is also practically negligible in all low-voltage circuits. The effect of resistance on the flow of electric energy in industry and industrial applications is limited to fairly narrow ranges. Since the resistance of the circuit consumes power, thereby lowering the efficiency of electric transmission, it is uneconomical to allow excessive resistance. Conversely, lowering the resistance too much requires greater expenditure on conductor material, which may also be uneconomical. As a result, the relative resistance, defined as the ratio of the power lost in the resistance to the total power, typically lies between 2% and 20%. The situation is different for the inductance, denoted as L, and the capacity, denoted as C. Of the two forms of stored energy, magnetic energy, equal to 1/2 of I squared times L, and electrostatic energy equal to 1/2 of E squared times C, one is often so small that it can be neglected compared with the other. Thus, an electric circuit can often be approximated as containing resistance and inductance only, or resistance and capacity only. In the so-called electrostatic machine and its applications, capacity and resistance frequently dominate the considerations. In all lighting and power distribution circuits, whether direct current or alternating current, such as the 110 and 220 volt lighting circuits, the 500-volt railway circuits, or the 2000-volt primary distribution circuits, the relatively low voltage renders the electrostatic energy, represented as 1/2 of E squared times C, very small compared with the electromagnetic energy. Therefore, in such circuits, the capacity C can often be neglected for most purposes, and the circuit can be treated as containing resistance and inductance only. Approximately equal magnitude are the electromagnetic energy, represented as 1/2 of I squared times L, and the electrostatic energy, represented as 1/2 of E squared times C, in high potential long distance transmission circuits, telephone circuits, and condenser discharges. This also applies to many phenomena resulting from lightning or other disturbances. In such cases, all three circuit constants R, L, and C are of essential importance. 10. In an electric circuit with negligible inductance L and negligible capacity C, no energy is stored, and changes in the circuit can occur instantly without any disturbance or intermediary transient condition. In a circuit containing only resistance and capacity, as in a static machine, or only resistance and inductance, as in a low or medium voltage power circuit, electric energy is stored primarily in one form. In these cases, a change in the circuit, such as opening the circuit, cannot occur instantly but happens more gradually, as the energy must first be stored or discharged. In a circuit containing resistance, inductance, and capacity, capable of storing energy in two different forms, the mechanical change of circuit conditions, such as opening the circuit, can occur instantly. In this scenario, the internal energy of the circuit adjusts to the changed conditions through a transfer of energy between the static and magnetic forms, and vice versa. After the change in circuit conditions, a transient phenomenon, often oscillatory in nature, occurs as the stored energy readjusts. These transient phenomena, involving the readjustment of stored electric energy when circuit conditions change, require careful study in cases where the stored energy is sufficiently large to cause serious damage. This is analogous to the readjustment of stored energy in mechanical motion. For example, while instantly stopping a slowly moving light carriage may be harmless, the instant stoppage of a fast-moving railway train, such as in a collision, typically results in disastrous consequences. Similarly, in electric systems with small amounts of stored energy, sudden changes in circuit conditions may be safe. But in high potential power systems with significant stored electric energy, any sudden change in circuit conditions requiring a rapid energy adjustment is likely to be destructive. Where electric energy is stored in only one form, there is typically little danger, as the circuit naturally protects itself against sudden changes by retarding the change through energy adjustment. However, in circuits where energy is stored both electrostatically and magnetically, the mechanical change of circuit conditions, such as the opening of the circuit, can occur instantly. In such cases, the stored energy surges back and forth between its electrostatic and magnetic forms. In the following sections, the phenomena resulting from the stored energy and its readjustment in circuits storing energy in only one form, most commonly as electromagnetic energy, will be considered first. Subsequently, electromagnetically and electrostatically will be addressed.